Good morning, students. Let us look at lecture number 4. Unit number 4. Combinational circuit designing. Or otherwise we write one thing, structure design. The structured design. So the structure design that we are going to use for combinational circuits. Combinational circuits. Right? Okay. Some of the combinational circuits let us look at here, which are able to implement in VLSI design. One is Parity Generator. The second one we look at is binary to gray, and gray to binary. Wise binary to gray and gray to binary. The next one we would like to discuss about is 4x1 multiplexer. Next one we would like to discuss about bus arbitration. The last one we will look at is PLA design. So these are the things that we would like to discuss in this particular structure design. Okay. So let us go quickly move on one by one. First one is parity generator. So what do you mean by this one? So if any input data that you give, okay, it finds the number of ones in that given number is even, then the logic output will be 1. If odd number of ones are there, then the circuit will produce 0 will be the output. So therefore what we can say that whenever you consider a digital system here, apply any set of inputs, for example A. So this input consisting of even number of ones, P is the output. If for example it will produce 1, so which means that it is an even number of ones are available in a given A. If it is produces 0, which means that the number of ones in the given number is off. Okay. So for example, something like this. For example, 1 0 1 1 0 1. I want to find out the parity of this particular data. For example, A is the data. I want to find out the parity of this one. How many number of ones are there in it? As by looking at this one, 4 ones are there. Therefore, P is equal to 1. Just a second. It is showing something like this. Okay. So how do we generate this one? What is the logical circuit inside of this one? That's important for us. Okay. So if you want to calculate, if you want to get the parity is 1, what we have to do, we have to initially take the 2 bits, right? So what is the value of this one? Just what is the operation is suitable for us? Exclusive OR operation. As we know that 0 0 is 0 1 1 0 1 1. If something like this, if even number of ones are there, that produces 0. Odd number of ones are there, it produces 1, right? It produces 1. Okay. So what we can say that here is that if first we should start from LSB to MSB. Let's do MSB. So first we have to take 2 digits and identify the parity between these two. If both are different, the output is equal to 1. Okay. And we have to take the parity information of this one with the next bit. With the next bit. Next bit is the 1, right? And we have to perform the XOR operation between these two. Okay, what is happening here? If both are same, then that value is equal to 0. That value is equal to 0. I think better we have tried the same color. Now I want to take, this is the 1. Next bit I have to consider here. So what is happening here now? Both are different, 1 will be the output. So therefore this is the parity actually. So this is the 1 parity. Now this is the parity bit of the information. So therefore, whenever we want to calculate something, previous parity information is required with the current signal, with the current one. So therefore, we take this one also, take 0. What is its parity between these two? Logic 1. This is the parity information. So we have to do with this number. So what is the value of this one now? 0. So that means if I'm performing the XOR operation, if even number of ones are there, 0 has come. But actually our requirement is 1 has to come. Okay, that means that what we can say that either you can take, this is even number of ones is 0, odd number of ones is 1 is also possible. This is a one choice. Otherwise, what we have to do is that we take the XNOR operation between them. Then if you use the XNOR operation, then that is the possibility is there. Are you agree with me? That's it. So therefore now we have to generate the information here. So what is the logical diagram that we have to consider? So which means that if the even number of ones are there, 0 will be the parity information. Odd number of ones are there, 1 will be the parity information. That's what we should know that. Okay. Now, what is the logical diagram for this? That means whenever we want to calculate the parity information, we should know what is the value of the I is required, A is required. Okay, A information is required. And the previous bit positions are also important for us, right? I minus 1, for example. So minus 1 I can consider. For example, previous information is minus 1, for example. Like that I have to consider. So therefore the current position. So if you want to write it the current position, better I will consider as this one. Okay, I is the current position. And I minus 1 becomes the previous position related information, which produce the current parity information. Right? So whenever we want to find out the parity information, these two informations are necessary for us. Okay. So what is the logic behind this one? What is the logic behind this one? Simply, this is simply AI exclusive OR with PI minus 1. That's it. Okay, this is for a single bit of information that we are talking about. If it is a multi-bit information, what the structure should look like? What structure should look like? Let us write like this. So for a n bit number, this is something like this. So I'm going to write the generalized structure here. Copy and then paste here. So just you have to understand here, the simple point is that, so this is the block diagram for a parity generator. Okay, it's a parity generator. So for this particular number, so we start from A0 to an. So n number of bits are there. For example, n bit information. Okay, so we want to calculate the P. Sometimes if you want to calculate P bar also can be possible to calculate. Doesn't matter. So complement of the previous one only. So therefore, what is the structure design here is that, so I have to take a bit by bit generation. Okay, so if you want to perform the bit by bit generation, what should I take? This is the generalized technique that we normally use. Copy and then paste here. So this is the way that we need to write. Okay, I hope you understand the problem is. Okay. If you are able to generate the PI, if you're able to generate the PI bar, it's okay. If you don't want to generate, it's not a problem. But usual practice is that it is necessary. Sometimes it is possible to generate the PI bar also. So with respect to the AI, so what does it mean actually? What do you mean by this one? Actually, we know that very well. This is actually AI bar into PI minus 1 plus AI into PI minus 1 bar antam. So that means we need to have A bar is required, A is required, A bar is required, PI is required, PI minus 1 bar is also required. That is the reason why it is usual practice we can generate both signals. Okay, are you getting what I'm saying? And we would like to discuss about PI and PI bar. So this is repeated for n number of bits, right? The same structure that I'm using here, the same procedure. So you can see here. So from bit by bit that we have done here, right? Bit by bit we have done. So that's the reason why what I'm doing here is that the structured. So this is the one structure. So the structural designing that we have to use. So we have to design one thing and we have to copy for multiple times. Therefore, according to the number of bits that we want to have. Okay, that's how we have to design the circuit. Okay, so everybody knows that what is the exclusive OR operation. For example, as I mentioned that, for example, y is equal to AI, okay, PI minus 1 bar plus AI bar into PI minus 1. Okay, so what is this the transistor level representation in CMOS and as well as NMOS technology? Very simple. Let us consider NMOS technology. So in the NMOS technology, what we can see that a depletion mode type of transistor is required and connected here, and the bottom transistors are we have so we should have both two transistors this side and another two transistors this side, right? So this implementation we have already seen extensively in the previous classes. So what we will get here now, for example, AI, I'm write it here, PI minus 1 I'll write here. See, please remember. Then AI bar I'll write it here, PI minus 1 bar I can write it here. So possibility is there. Okay, this is actually what we will get here now. AI into PI minus 1 bar plus AI bar into PI minus 1. Actually, this is what we want to get it. So, but if you write this A bar here and then something like this, if you write, okay, what will happen? This whole bar will come into the picture. Again, what I have to do, I have to take the inverter at the output side. Instead of doing that, what I'm doing here is that I don't want to keep the P bar here. So, okay, just I will write P here only. Here I have P bar, I can write. So therefore, this is actually A bar, B bar, something like this, it will be happen. So this is the whole bar only, right? So the whole bar in sense, what will I get? It is simply AI into PI minus 1 bar plus AI into PI minus 1. A bar. So that is what the answer that we will get. Exclusive OR operation, XNOR operation, complement is XOR, XOR complementation is XNOR. Okay, so that's how we'll get it there. Are you agree with me? So how I have done this one? Okay. Now in the CMOS implementation, what I can do it, what I'll do for the CMOS implementation. There is the CMOS implementation. Just in a CMOS implementation. So the bottom transistor for PMOS, what we can do it. PMOS transistor I should consider. So this is how we have to do it. This is called AI. This is called PI minus 1. This is AI bar. This is PI minus 1 bar, right? So this is connected to VDD. This is connected to VDD. And bottom is as usual. Okay. So what I can do is that I'll copy this one. Copy. And I want to paste it here. So that's it. Okay, so here these many things that we have to do. So this is called Y output. This is CMOS implementation. How many transistors are required here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 transistors are required here. So A bar is also we have taken, right? PI bar is also we have taken. Here how many? 4, 4, 8, 8 plus 4, 12. So 12 transistors are required in this case. But in the depletion, we find some kind of difficulty ratio we have to maintain. But in CMOS implementation, when we need not maintain the ratio. Okay, what now in a CMOS circuits, we have to draw the stick diagram and layout for this one. Okay, so what is the stick diagram? Please go through it once. Stick diagram. So I hope the color diagram is available. I will show you that. Possible. Please wait for a second. I will check it. The color diagram is there or not. If not, I have to draw. But of course, you know very well how to draw this stick diagram for this. Okay. Please try to do it. There is no color diagram, I hope so. Yeah, there is no color diagram. We have a monochrome diagram is available. So just for the sake of understanding, I want to show how to draw the stick diagram for this one. We know very well how to draw the stick diagram. Previously, we have already seen. Okay, so I have to copy this one and I have to show it here. So this is what the stick diagram. Okay. So this is what the stick diagram that we have to do. So here you see, observe that one. Here we have PI and PI bar. Okay, sorry, I'm extending. Sorry, this is not like that. PI AI bar. Next, this is actually this is what PI bar. So he has taken here. That means metal they have considered and extended, and AI. Okay, therefore they have directly what they have done here. Actually, they have implemented XOR gate here. They have implemented XOR gate by using the PI minus 1 and AI bar, and this side is PI minus 1 bar into AI. They have taken. That's the reason why they had to consider the NOT gate. They had to consider the NOT gate at the output side. So, but we haven't done like that. Just we have directly used in this way. Okay, either one is possible, but I would like to do in this method. Therefore, it is actually, please remember that here's the PI is actually, so PI minus 1 bar into AI plus bar plus, now what will be the output here now? Oh, the XOR gate they have considered, right? So they have considered the XNOR gate. So because they were in the textbook, what they have mentioned that they would like to mention this is here is actually logic 1 for even, logic 0 for odd. Okay, that's the reason why what they have done, they have used the exclusive OR gate, as we have mentioned that this is meant for XOR gate, but they have used the XNOR gate. Okay, so either one is possible to consider, whether you take the parity information 0 for the even, odd for the one, or other even 0 for the odd also can be possible. So please identify this differentiation. Okay, this difference you please identify. Okay, so according to this point, we got this. So I think better I should write here is we worked based on we worked based on XOR gates. Please remember, in the textbook they have used it for XNOR gates. Okay. Next one is binary to gray and gray to binary conversion. What we have to do is that, for example, B2, for example, B3, B2, B1, B0 is there. How do you get the binary gray code for this one? How do you get the gray code for this one? Just we have to take the first MSB bit is same as this one, that is called G3. And if you want to get the Z2 value, what I have to do, I have to perform the XOR operation between these two, right? So then only we will get B2. So if we take another exclusive OR gate here, then we will get G1. Then we will get Z1. So if you perform the XOR operation between these two, what we will get? We have G0. Therefore, what I can write now here is that simply it is an exclusive OR operation only. It is B3. If it is Z2, what will happen? If it is Z2, what will happen? It is B3 plus exclusive B2. What is G1? G1 is B2 exclusive B1. So G0 stands for B1 is exclusive B0. Okay, this is how we have to write. So therefore, what I can do here is that, what is the logical diagram? What is the structure design for this one? Bit by bit thing that we have to do it. So here is, if we consider B3, we can generate G3 here, so comfortably. But we have to take one particular block. So we have to take one particular block. Okay. So for this one, we need B3 is required and B2 is also required. Therefore, we should generate, we are able to generate G2. Okay. It is simply an exclusive OR gate. So this structure we have to use repeatedly, right? So the structure we have to use repeatedly. How many times I should use? Copy. 3 times I should use. So this is what the structure that we have to use it here. Okay. So it requires what it requires? It requires that B2 is required and it should generate G1. So this generate B1. So it should generate here. We should apply here and we should generate G0 here. So agreed. So this is called B1. So take the whatever the exclusive OR gate that we have generated here, whatever the XOR gate that we have generated here, we have to take 3 times and we should generate the gray to binary code conversion. Okay, the similar concept is applicable. Of course, we are not going to do this. What is the circuit diagram for this one? Because it is a replication of the same thing only. Okay, if you want to have a clear-cut idea, what I have to do is that I have to consider 4 times. Sorry, 3 times I need to consider, right? So better I have to take a very simple diagram. Okay, so this is how we do it. Okay, so fun time, copy. So this is how the structure design is all about. Okay, so this is the second one, and the third one. Okay, so just only one time process is required. The remaining things just we have to copy all those things. Of course, by the by, just you have to identify what inputs are required. Please do it on your own. Okay. So what output we will get, how what inputs that we should apply here. So like this, we have to generate the VLSI circuits, right? So apply the appropriate input signals to this and get that what is required for us. Okay. So this is for this one. This is for this one. This is for this, and this is for this. Okay. I hope you understand the concept. Next, similar concept is applicable for the gray to binary also. What is the concept behind the gray to binary? Gray to binary. So if you have a gray code, for example, G3 available, G2 available, G1 available, G0 available, 4-bit gray code. So how do we get this one? B3 is directly B3 directly from G3 only. But we have to take the exclusive OR gate between these two and generate this one. This is called B2. Take these two and perform the XOR, B1 will generate. Take this one and do this with this, will get generate B0. Okay, therefore, what is the total value of this one? How do we generate this mathematical equation? B3 is nothing but simply a G3. Okay, B2 is simply B3 exclusive OR gate with G2. Okay, and B2 is B1 is nothing but what is the value? B1, sorry, B2 exclusive G1. B0 is nothing but B1 exclusive G0. So that's it. And the structure design that we have to do it accordingly. Just we have to make the connection among that one. And the same procedure is applicable for this one also. Okay. This is all about gray to binary. So just only the circuit implementation is required in this one. Nothing else in it. Okay. Next one is, let us consider multiplexer. 4x1 multiplexer. So what we know about it, so we want to implement by using the switch logics. By using the switch logics that I want to implement. Switch logic is nothing but we use simply a pass transistors. Okay, pass transistors. So what is the pass transistors we normally consider? For example, so apply the control signal here, but input is we need to apply at one end, and we have to see the output at the other end. So initially the inputs are applied. So in this case, inputs are applied at this gate of the transistor. Okay, but here we would like to apply the inputs at the one terminal of the source or drain. Okay. Now in this approach, how do we look like a 4x1 multiplexer? So this is how. So having, for example, I0 is one input, I1, I2, and I3. So we have S0, we have S1. So it will produce Y. It is called 4x1. What is the mathematical equation for this one? Everybody knows from the fundamentals, S0 bar into S1 bar into I0 plus S0 bar into S1 into I1 plus S0 into S1 bar into I2 plus S0 S1 into I3. So we fundamentally know very well. Now, but how do we implement this one in VLSI point of view? So the logical point of view, as I mentioned, that switch logics that we would like to do this one. So what I'm going to do here is that we take a MOS transistor as a pass transistor, and NMOS transistor I would like to take. Here S0 bar I would like to consider. So I want to apply the input is here. I0 is I want to apply here. So what we will get here is that it is nothing but I0 into S0 bar will be the output will get generated. Okay, so just multiplication of the gate and so this terminal side, you get this one, and you take another transistor S1 bar, so that will be multiplied here as well with S1 bar. That means I0 into S0 bar into S1 bar. Agreed? Okay, so this is the one output that we would like to do, we would like to get. So how many these structures are required? How many this structure is required? Or operation performed 4 times I need to require. I need 4 times. So I can substitute this information 4 times. This is the 1. So this is the 2. This is the 3. Okay, so 4 times I need to have. So, but provided that what input signals are required, S1 is required, S0 bar into S1 is required. Here it is required. Both are not required. But one thing is very important to remember. Here is inputs are I1, I2, I3. Okay, so I think better I should remove these kind of things for the sake of simplicity. I will write at the end point only. So all these things need to be added, right? All these things need to be added and take a common point that is called Y. Okay, so what is the output that I'll get here? S1 into S0 bar into S1. Okay, by the way, you please understand that one S0 bar is MSB bit, it is a LSB bit. You please remember that. Usually we will write S1 is MSB and S0 is LSB. Please try to understand what I have written. S0 into S1 bar. Therefore, I3 into S0, S1, right? This is how we need to write. Is it right? So this is one of the structured way of implementing your 4x1 multiplexer. If you want to do this one with the Cmos implementation previously, it takes a lot of time. Okay, this more number of transistors are required here. But here, with a less number of transistors, it is possible to do this one. Okay, this is the circuit. This is the circuit. What is the stick diagram then for this one? Yeah, fortunately, we have a stick diagram in our textbook. We consider that. So we have to consider that. So by the way, have you seen that the textbook? What is there inside? What is the backside of the textbook? You can see at the last pages, the color codes are available. Okay, you have to use the color codes. So this is how it looked like. Okay. What is this? It is not showing. Yeah. So this is what we can write here. So you observe that how do I written? How they have drawn? So this from this point to this point, from this point to this point is a diffusion line. Okay, source and drain are diffusions only, right? Agreed. So we have a one diffusion line here, another diffusion line, third diffusion line, fourth diffusion line. So when a polysilicon is called the diffusion line, the transistor is formed. Okay, the transistors are formed here. So therefore, for the connection purpose, we use the metal lines over there. For these are the metal lines for I0, S0, S1, S2 connected there. So that's it. So this is the stick diagram for the given piece of circuit. Okay, that's it. So just only for the implementation part, as I mentioned that we are discussing about only the implementation part. The next one is bus arbitration. Sorry, it's not right. Bus arbitration, which is nothing but a priority encoder. So parity, not priority device. So just a number of bits are there. Just we have to give the priority among that one. So how do we do that? What is the main intention between these two. Okay, let us do this one. Yeah, before. So for example, this is the circuit is available. Okay. We have this circuit is available in our hand. The block diagram of this one. Okay, so what is there here? So I have a n-bit data here in my hand. So it is an n-bit data. So I have to generate the n-bit output. I have to generate n-bit output. What is the logic behind this one? How this n-bit output will be generated? How A1 of P is generated, A2 of P is generated, A3 of P is generated, how it will be generated? So based on this truth table. So it is simply a parity between the things. Priority between the things. So what do you mean the priority between the things is OP, and I want to paste it here. Okay, so what this table says that, you please remember, please understand this concept. So whenever the highest bit is available, for example, whenever the AN bit is available, that means MSB bit is active high, you don't want to forget, you forget about all other things. Okay, so you should generate the output is equal to 1 for A and P. Okay, and remaining all are zeros. Remaining all are zeros. Remaining all are zeros. Agreed? So therefore, what I can write now here is that AN of P is nothing but simply AN. Agreed? Irrespective of the other things. Next, for example, AN minus 1 of P. That means, for example, this one I want to get it. Okay, what I have to do? So, this must be 0 and then this must be 1. And remaining things I do not worried about it. Remaining things I don't want to worry. I am not at all worried about this, right? Agreed? Then it will produce the one here. Sorry, it will produce the one here, and remaining all are zeros, right? Therefore, AN minus 1 is nothing but what is happening here. AN value must be complemented. That means that must be 0. And not only that, then AN minus 1 must be generated, must be there. Then only it has to perform. So like this, we have to generate like A0 of, I think A0 and A1. So A1 of P, if I want to get it, I have to start from A0 bar, AN minus 1 bar, so on up to A2 bar, A1, sorry, A2 bar, A1, something like this. So therefore, this is the logical representation. It is called logical representation. So how do we implement the circuit now? Let us implement the circuit in this way. Okay. Let us implement the circuit in this fashion. Okay. So directly stick diagram they have given in the past transistor notation. Please understand that. I will show you, I will tell you what is exactly this. So what I have to do here is that, see, the past transistor implementation they have done. This is a stick diagram actually. It is a stick diagram. Stick diagram. So what does it mean here? Simply one direct line is available for AN from AN of P, then will generated. What about this second case? Okay, so what is happening here is that I have to take, for this one, I have to consider AN bar is one transistor here. Okay, so, and of course, there is a problem with this AND operation between these two. Something like this, they will be generated. So 0 here is the one, AN minus 1 is required. Okay, therefore AN bar is required. Therefore, this is also AN bar is required. So this is what actually they will generate for A minus 1 of P. Generally, in the previous what we have done, so by using this approach, for example, suppose x is here, y is here, it is x dot y I have written, but actually we don't get x dot y, provided we have to use an extra transistor at the ground terminal and connected here with the y, then only we'll have proper x dot y will be generated usually. Okay, this concept we'll discuss after some time, but this is how we have to understand that about the AND operation. So this is the theory that they have used at this point of time. Okay, so like this they have done. Similarly, we have to generate for this one. So what I have to do is that 3 lines are required. So an minus 1 is required. So 0 is required for this one. 0 is required for this one. Okay, and an minus 1 is also 0 is required. Okay, but what we need 1 is required for this one. Okay, so that is how we have to do it. Okay, so that means 3 1 diffusion line is we have used, 2 diffusion lines we have used, 1 and 2, 3 diffusion lines we have used here. Like this, depending upon the number of inputs in a given structure, the structure is expanded like this. So next one we have to use the 4 diffusion lines. Next we have to use 5 diffusion lines. We have to expand something like this. It is not a regular structure. Okay, what we observe that it is not a regular structure. If it is not a regular structure, it is not possible to implement in VLSI circuits. Not implement. Implementation is difficult. So what we have to do is that we have to convert this structure into a different method. So therefore, that is called cellular method. Cellular method. So in this cellular, by using the cellular method, okay, so we have to convert this one into a structural way. Okay, how do we get this structural? We have to convert this irregular structure into a regular fashion by using different methods. How do we do this one? So this is the structure that normally we use for this. So this is the one. Okay, so I just want to copy this here. Okay, so this is the regular structure I have to consider. So what is this one? We can call it as, so I'm going to consider here is a grant line. So G stands for grant line. Grant line. So therefore inputs are available here, an minus 1, so on up to ai. Okay, so it has to generate an plus 1 and of course grant line. For example, what does it mean? For example, I'm saying something like this. For example, a is equal to 1, for example, then immediately an of p is equal to gi plus 1 has to generate. Okay. Whatever maybe okay, intermediate signal what I have to do is that in this case only we consider, for example, this one only we consider. Okay, what is there in it? We take this is a not a minus 1, a and first bit chosen. This is what I would like to discuss about it. And if suppose higher MSB bit is 1, then the output must be equal to grant line should be. That means logic 1. So grant line in the sense that logic 1 will be generated. If not, for example, an is equal to 0 then an of p is equal to 0 it should be. Then what we have to say that we are giving the provision to the other state. So we have to give the access to the other block. Okay. So what is so okay. Better I'll write here GI also. And this one, what about the GI then? J is equal to 0. That means that we don't want to consider the input for the other succeeding stages, right? Other succeeding stages does not give a grant because A is equal to 1. For example, an is equal to 0. We have to give the grant to the next one. Okay. So A is equal to GI plus 1. It should be like that. So therefore, that is what has to happen. So if an is equal to 1, output has to generate, but don't give it to the access to the other one. That means we have not given the access to this one. If an is equal to 0, that means that I'm not applying any this signal. That means parity will be given to the next one. So therefore, an of p is equal to 0. So output must be 0. Then this value has to be generated. So therefore, it has to be generated as well as this has to be generated. Right? So that is what the logic behind this one. So therefore, the simplest understanding about this one is, so how do I write now what about A and GA plus 1? Okay. So in terms of generic notation, what is the generic notation is that AI is equal to 1 అయితే AI of P is equal to GI plus 1 అవుతుంది. And GI is equal to 0 అవుతుంది. Next, AI is equal to 0 అయితే AI of P is equal to 0, but GI is equal to GI plus 1 అవుతుంది. So therefore, what I can write now like this, AI of P is can be written as AI into GI plus 1, we can write it. Therefore, AI of P is equal to, sorry, what I can write for GI of P, GI is nothing but AI complement into GI plus 1 అవుతుంది. That's what we are going to write. So this is the logical implementation that we have to do instead of this methodology. Instead of this methodology, I have to go for this is the one. So therefore, this is the structure. Therefore, I have to implement this only this structure. I have to implement only this structure and replicate a number of times. How many number of times are there that I can do it? So this is the structured approach that we have to follow. Okay. So for this one, I will write a simple diagram. So please wait for 2 minutes. I'll complete it. Just the circuit diagram. What is the circuit diagram for this? Okay. So copy and then paste it here. Please remember this circuit is very, very important for us. So this is the generalized block. That means this is usually we use this one. Okay. So one particular, that means this is simply implementation of the circuit only. So this implementation is done here in this way. Okay. So for one particular block. Okay. So what we do is that, so according to this one, if A is equal to 1, for example, we take one pass transistor here. Okay. So GA plus 1, this is actually plus 1. GA plus 1 will be the output to this one. That is what we have to done here. Clear to all of you? So during that one, what about the GA? GA must be equal to 0. How do you make that GA is equal to 0? What I have to done this one? I'm going to use another transistor here, the same input. What is that input? A only. So A is equal to 1 and 0 will be transferred to this one. 0 will be transferred to this. So usually two buffers that we normally use for any circuit implementation for improving the driving capability. For the timing, don't consider that one. But anyway, consider or not, doesn't matter. GI will be generated as 0 now. Is it clear to all of you? So therefore, this is what happening here. This implementation is done in this way. So if A is equal to A into GA plus 1, provided that GA is also must be 0. So that is how we have done here. If A is equal to 0, then what will happen? That means the input is available here. That means 0 means this is off. So meanwhile, what about the conditions of this one? It is off. It is off. Okay. Please remember that first case, A is equal to 1. Now if A is equal to 0, then what will happen? So this transistor becomes on, this is on, this is on, this is off, this is off. Okay. So therefore GI is directly go to this particular GI. GI plus 1 is directly go to the GI. Okay. Provided that this must be 0. So we make this 0 is something like this. This is making this one is equal to 0 in this way. So that is how we have to generate the circuit diagram. Okay, so therefore this we have to use how many times, how many number of bits are there, input bits are there, those many number of these blocks are required. So this is called n-bit arbitration network. It is simply a parity circuitry, priority circuitry. Which bit has the highest priority, which one bit has the lowest priority. priority that we have to generate it here. Okay, so then PLA implementation is there. You please go through the PLA implementation at the back to the circuit. Otherwise, we will discuss in the next class. Okay, we stop it here today, and remaining things will